In this video, we're going to have a look at the Clausius Clapeyron equation. Shown here, the equation is useful for estimating the vapor pressure at any temperature, or we can use it to estimate the heat of a phase transition from the vapor pressures measured at two different temperatures. Before we start, it's useful to note that the pressure can be any unit. The R is going to be 8.314 joules per mole per Kelvin, and the temperature has to be in kelvins. Before we start, I just want to note that this is one form of the equation. This is another form, and this is yet another form. Changing the order in which the temperatures are listed creates a negative sign out front of the delta H. You can see it right here. Changing the order of the pressures, in other words, putting P1 over P2, creates a negative sign out in front of the natural log. Doing both offsets the negatives. So none of these equations are wrong, and sometimes you'll see one versus the other depending on what textbook or website you're looking at. Any of the three will work. For general chemistry, we need to be able to solve for any of the variables that you see here. That includes the pressures, the delta H, R, or any of the temperatures. In order to do that, we need to have a good understanding of the properties of logarithms as well as basic algebra. If you're solving for a pressure, the best way to do that would be to use the temperatures that you're given and solve for those completely. So for this right here, you want to go ahead and solve, plug in your 1 over T1, your 1 over T2, and get a number for this. If you're being asked to solve for a pressure, then it usually means that your delta H and your R will already be known. So using all of these numbers, it's possible to solve all of this for just one number. And so we'll say that number is 4. From there, we need to look at the natural log portion of the equation. So we're going to take natural log of P2 over P1 equals 4. And we're going to be able to separate these two by utilizing a property of logarithms. And that property is going to allow us to do this. Natural log of P2 minus natural log of P1 equals 4. So at this point, we probably have one of the two pressures. And so if, let's say we have P1, we want to go ahead and just get a number for that. So we're going to go ahead and plug in P1, take the natural log of that, and we're going to put that into our calculator, get the number, plug it into the equation. And then how do we solve for the natural log of P2? To solve for P2, we want to take the inverse natural log of both sides. So taking the inverse natural log of the natural log of P2 is just going to give us P2. And this is going to give us the natural log of 4 minus whatever number we got for the natural log of P1. If we're asked to solve for the temperature, it's a little bit more complicated, still not bad. In the case that we're given two pressures and only one temperature, we'll be given delta H of vaporization. So that means that we can get a number for the entire left side of the equation, which is the natural log of P2 over P1. And the way that we do that is just take P2 divided by P1 and go ahead and get the natural log of that number. We can also get a number for the delta H over R. So put those two numbers in your calculator, divide them, you'll get a value for that as well. So assuming we have a value of 4, how do we solve for either the T1 or the T2? So the first thing we'll do is we'll use algebra to just distribute the 4 to both of these terms. One of the two temperatures we're going to know. Let's say we know T1. Let's say T1 is 100. Once we've done that, we're going to have a number for the 1 over T1. We can multiply that times the 4 in front of it, and we get 4 equals 1 over 25 minus 4 times 1 over T2. We want to take all the numbers that don't have a variable and move them to one side of the equation. So we're going to get 4 minus 1 over 25 equals negative 4 times 1 over T2. Next, we're going to solve the left side of the equation and get a number for that. We can multiply the 4 times the 1 over T2, and when we do that, we're going to get negative 4 over T2, and all of that's going to be equal to 38.96. At this point, we're going to multiply both sides of the equation times T2. On the right-hand side, the T2s are going to cancel. On the left-hand side, the variable is going to remain, but the variable will be on the top, so it's going to be easy to solve for now. So to solve for it, we're just going to divide by 38.96 on both sides, and that's going to cancel on the left, and on the right-hand side, we're going to get the value of T2. Now, in this example, I got a negative number, but that's not going to happen if you do it correctly with a real problem. In this problem, I just was showing you how to solve for the temperature. You will use the same strategy, plug in the values that you have for your temperatures, for your pressures, and your enthalpy of vaporization. So let's look at a real problem here. For acetone, the normal boiling point is 56.5 degrees Celsius. Enthalpy of vaporization is 31.3 kilojoules per mole. The question wants to know, what is the vapor pressure of acetone at 25 degrees Celsius? So for this problem, we can use the Clausius Clapeyron equation. We have to do some converting, though, because the temperatures have to be in Kelvin. They've been given to us in degrees Celsius. We also need to convert our delta H of vaporization into joules. And the reason we have to do that is because the R value that we're given is going to be 8.314 joules per mole per Kelvin. So we either need to convert the 8.314 joules per mole per Kelvin into kilojoules, or convert our enthalpy of vaporization into joules. Now notice that the problem has not given us any numbers for the pressure. And this is because it does tell us that the normal boiling point for acetone indicates that it is 56.5 degrees Celsius. Normal, when we use that word in chemistry, the word normal indicates that's standard pressure. So that means that at 1 atmosphere, or 760 torr, or 760 millimeters of mercury, or 101,325 pascals, that's going to be standard pressure. So the pressure, one of the pressures that we're going to put in is going to be 1 atmosphere, or we can choose 760 torr millimeters of mercury, or 101,325 pascals. So that's going to be one of the pressures. So that means that one of the pressures, we'll call it P1, is going to be 760 torr. I'll choose torr. You could choose any of the units you wanted. Now, for the T1, I'm going to use the same set of conditions. So if my pressure, my normal boiling point is going to be at 760 torr, that means I'm going to want to use the temperature that corresponds to that condition. So that means my T1 is going to be 329.65 Kelvin. And it says, what is the vapor pressure of acetone at 25 degrees Celsius? So basically I'm going to be solving for P2. We don't know that. And we're going to be solving for P2 at a temperature of 298.15 Kelvin. So now I'm going to plug in my values. Now with all these values plugged in, I'm going to completely solve it for the right side of the equation, get a number for that. So the value I got is negative 1.189. It's okay to get a negative value here. As long as we solve it, the pressure should be positive. The next step, I'm going to separate my pressures using the properties of logarithms. And I'm going to go ahead and take the natural log of 760. And I'm going to move the negative 6.633 to the other side. And finally, I'm going to take the inverse natural log of both sides. And so my answer when I solve that is going to be 231 torr.